Neutron stars, the most extreme objects in the universe, except for black holes. Since its origin in the Big Bang 13.8 billion years ago, the cosmos has unfolded a story of majesty and wonder. There's much we think we grasp, but so much more that leaves us in the dark. Our universe, simply put, is so vast that we have barely scratched the surface of what's out there. There are an estimated 400 billion stars in the Milky Way alone, and more stars in the observable universe than there are grains of sand on Earth. When we dive into the fascinating world of stars, we find something that shouldn't exist. But there they are. Born from the cataclysmic death throes of massive stars, these spooky stars are some of the universe's most extreme objects. They are dense, really dense. So dense that a single teaspoonful of their material would weigh 1 billion tons on Earth. That's as much as 166 Great Pyramids of Giza. What's more fascinating, defying our theories about dead stars, these bizarre stars can live forever. Scientists call them neutron stars. NASA estimates that there are as many as 1 billion neutron stars in our Milky Way galaxy. The majority of neutron stars discovered thus far are young neutron stars that sweep energetic radiation over the Earth as they rotate at incredible speeds. Older neutron stars, which have had billions of years to slow their spin and cool, are less conspicuous but no less fascinating. As Large Area Telescope Science team member David Thompson of NASA's Goddard Space Flight Center said, "With neutron stars, we're seeing a combination of strong gravity, powerful magnetic and electric fields, and high velocities. They are laboratories for extreme physics and conditions that we cannot reproduce here on Earth." Join us as we dig deep into the secrets lurking within the densest and most mysterious objects in the universe. Think about it. In the depths of space lie dead stars, each containing more mass than the Sun but crammed into a space the size of a city. Neutron stars are so tightly packed that a single teaspoon of their contents would weigh more than Mount Everest, or about as much as every human that has ever lived. What's more, neutron stars spin multiple times a second, are highly magnetized, and emit rotating beams of radiation like celestial lighthouses. How do neutron stars form? Neutron stars are the remains of the cores of massive stars that have reached the end of their lives. The life of a normal star, no matter its size, is a balancing act between the inward push of gravity and the outward push provided by photons generated as they conduct nuclear fusion, the forging of heavy atomic nuclei from light nuclei at their cores. When stars run out of hydrogen to fuse into helium, they reach the end of their main sequence of nuclear fuel-burning lives. The outward energy ceases, and gravity wins out, causing the core of the star to collapse in on itself. As this happens, nuclear fusion in the outer shell of the star continues, causing these outer layers to puff out. These shed outer layers cool around the still collapsing core, which, if it is massive enough, will begin a new round of nuclear fusion, forging helium into heavier elements like carbon. Even stars with masses between 10 and 20 times that of the Sun reach a limit to the heavy elements they can forge, usually ending up with a core of almost pure iron. Even this heavy element isn't dense enough to prevent massive cores from further collapse. As this occurs, the gravitational pressure is so intense that the negatively charged electrons and positively charged protons that comprise the iron nuclei in the stellar core are crushed together, creating a sea of uncharged or neutral neutrons. Some massive stellar cores are, at this point, saved from further collapse by a quantum phenomenon called neutron degeneracy pressure. This occurs when such a density is reached that neutrons can no longer be packed any closer together, leaving them as neutron stars. What's notable is that a neutron star is 90% neutrons. Effectively, each one is a giant, city-sized atomic nucleus. A neutron star has a similar structure to our planet, with an atmosphere, crust, and core. But what goes on inside is very different. The gravity of the neutron star maintains an atmosphere of hydrogen, helium, and carbon heated to around 2 million degrees Celsius. This atmosphere is just a few thousandths of a millimeter thick. The outer crust is made of a mixture of electrons and atoms that have had some or all of their electrons removed, known as ions. Here you will find superconducting protons. A superconducting material offers no resistance to electrical current, so the current can flow through it without losing any energy. The least understood part of a neutron star, the inner core, could be made of a soup of quarks, the particles that make up protons and neutrons. The neutron star's magnetic field holds a lot of sway in this region. It could help fragment the crust and generate starquakes. Material in the inner crust takes the form of electrons, neutrons, and atomic nuclei. Neutron stars exist in space because of a delicate balance of forces. On one hand, you have gravity trying to collapse the star. Research published in July 2021 found that the gravity of neutron stars is so extreme that mountains on their surface can barely reach a millimeter in height. But resistance to gravitational collapse comes in the form of something called degeneracy pressure. This pressure is generated because there comes a point when it is too hard to squash nuclear material closer together, and so the two opposing forces balance each other out. This means that the most massive neutron stars should also be the smallest. More mass means stronger gravity and therefore a more compact, tightly squeezed object. At least, that is how it is supposed to work. Imagine the surprise for astronomers when in 2019 they stumbled across a seemingly impossible neutron star. This neutron star currently makes no sense. A neutron star with a density far greater than its vast size should allow. Explaining its existence wouldn't just answer important questions about neutron stars that we've been asking for decades. It could also tell us more about nuclear physics and gravity to boot. The neutron star in question is called JASA 74 and sits 600 light-years away in the constellation of Camelopardalis, the giraffe. Like many stars, it exists in a pair or binary star system. Its partner, 662 Iri, is a white dwarf, another type of dead star. According to Anna Watts from the University of Amsterdam, who is part of the team that's been studying JASA 74 and other neutron stars, as these objects spin, their brightness changes because there are hotspot regions on their surfaces. We can use this characteristic to build up maps of those surfaces. To accurately chart the surface detail of an object the size of London from a distance of over 600 light-years or 34 quadrillion kilometers is quite some feat. It takes 3 to 4 weeks of observations over the course of a year. These surface maps are one of the tools Watts and her colleagues use to estimate the mass and size radius of neutron stars, such as JASA 74. It turns out that JASA 74 is the most massive neutron star we've ever found, tipping the scales at 21 times the mass of the Sun. So it should also have the smallest radius. Except it doesn't. It's just as wide as another neutron star with only 2/3 as much mass. That means the material inside JASA 74 isn't as compressible or squishy as astronomers tend to refer to it, as they thought. This potentially gives us clues about what's going on inside the core, which is important because, of all the layers a neutron star has, the core is the least understood. Why form a neutron star and not a black hole? Back to the formation of neutron stars. If this process of neutron star birth sounds familiar, that could be because it is also the path that a massive star takes to become a black hole. The question is, why do some stars birth neutron stars while others leave behind black holes? The key difference seems to be the collapsing stellar core possessing enough mass to exceed the protection that neutron degeneracy offers. Neutron stars currently, scientists aren't exactly sure where the delineating line between black holes and neutron stars lies. This uncertainty exists because the physics inside neutron stars remains difficult to investigate. The heaviest known neutron star has a mass equivalent to around 25 times the mass of the Sun, while the lightest known black hole has a mass of around 5 times that of the Sun. Thus, there is a mass gap between these two types of dead stars, which scientists are currently attempting to narrow. It is in this gap that the line between one path and the other must lie. Researchers currently think that the dividing line between neutron stars and black holes lies much closer to 3 times the mass of the Sun than 5 times the mass of the Sun. As the main difference between a black hole and a neutron star is mass, it only makes sense that neutron stars accumulating material from a binary partner could eventually become a black hole. The process of mass accumulation could take as long as millions of years, but the eventual transformation from a neutron star to a black hole takes less than a second. Will the Sun become a neutron star or a black hole? While the line between neutron stars and black holes is vague and poorly defined, the Sun does not have enough mass to become either. It will end its life as a white dwarf. The line between the stellar remnant that our Sun will become a white dwarf and a neutron star is much better understood. When the Sun reaches the end of its hydrogen supply in around 5 billion years, the outward pressure protecting against gravitational collapse will cease, and its core will collapse. After passing through a red giant phase, during which the Sun's outer layers will swell out and swallow the inner planets, including Earth, the Sun's core will be left as a smoldering white dwarf. Just as neutron stars are prevented from becoming black holes by neutron degeneracy pressure, white dwarf stars are protected from further collapse by electron degeneracy pressure, which stops electrons from being crammed any closer together. Electron degeneracy pressure is much weaker than its neutron equivalent. Astrophysicists also have a better idea of the masses needed to overcome electron degeneracy pressure than they do for neutron degeneracy pressure. To eventually become a neutron star, this white dwarf would have to exceed what is known as the Chandrasekhar limit, which is generally considered to be 1/4 solar masses. According to the Sao Encyclopedia of Astronomy, this means that the core of the Sun alone would have to have 1/4 times the total mass of the Sun. The Chandrasekhar limit mass, first predicted by Subramanian Chandrasekhar in 1931, has so far corresponded well with observations of white dwarfs, as we are yet to find a stellar remnant of this type with a mass above 1/4 solar masses. NASA estimates that the Sun would have to be 10 times more massive to end its life as a neutron star or 20 times more massive to leave behind a black hole. To consider how dramatic and violent the near-complete gravitational collapse that births a neutron star is, one only has to look at the material that it creates and the dimensions of the object it comprises. The collapse of massive stellar cores results in an object that has from 1 to 2 times the mass of the Sun, but only has a width of between 6 and 12 miles. Imagine the Sun reduced in size until it is a sphere that sits comfortably within the city of New York, which is 35 miles wide. Being reduced from a diameter of 870,000 miles to just 12 miles would have a striking effect on the material within it, and this is definitely the case for neutron stars. NASA estimates that a single sugar cube comprised of this neutron-rich matter would weigh around 1 trillion kilograms, or 1 billion tons, if it were brought to Earth. That's a sugar cube that weighs as much as 3,000 Empire State Buildings or the entire human race. This makes neutron star matter the densest material we can see in the universe. This density has another effect. Neutron stars are so dense that the speed it would take to escape their gravitational influence is half the speed of light. As a consequence, the gravity of neutron stars is so strong that, according to NASA's Goddard Space Flight Center, if a marshmallow would drop to the surface of one of these exotic stellar remnants, it would accelerate so quickly that when it struck the surface, it would release energy equivalent to the detonation of 1,000 hydrogen bombs. While marshmallows don't tend to rain on neutron stars, gas stripped from companion stars in binary partnerships with these extreme stellar remnants often does. When this gas hits the neutron star's surface at speeds as great as millions of miles an hour, it creates powerful firework displays in X-ray light that flicker in intensity thousands of times per second, or perhaps burst only once every few years. The density and gravity of neutron stars aren't the only things that make them the most exotic objects in the universe. They also have some other extreme characteristics. When neutron stars are born, the conservation of angular momentum results in them spinning at incredibly rapid speeds. To understand why this is the case, think of an ice skater and a spin. As they draw their arms in, the skater's rotational speed increases. A similar thing happens when the diameter of a stellar core shrinks as it undergoes gravitational collapse. The resultant young neutron star spins faster and faster, reaching speeds as great as 60 rotations per second. According to the Swinburne Center for Astrophysics and Supercomputing, many neutron stars slow as they age, reducing to rotations of around 8 times per second. However, the situation is different for neutron stars that are stealing stellar material from a binary partner. This material carries with it angular momentum, and thus this transfer of matter can actually speed up, or spin up, the rotation of neutron stars. This can result in some neutron stars rotating as fast as 600 or 700 times per second. The fastest spinning neutron star on record, discovered in 2006 according to the National Radio Astronomy Observatory NRAL, is PSRJ 17748-2446 AD. That one event from August 17, 2017 remains the only directly observed neutron star merger to produce heavy elements. This has taught us something remarkable and important. Our initial estimate that around 100% of the heaviest elements in the universe was produced from neutron star mergers is no longer consistent with the data we've collected. Something else beyond what we've seen so far must be at play. 3 possible explanations immediately spring to mind, but all 3 have complicated problems. Perhaps the neutron star merger rate creating these elements was greater in the past than it is today. Perhaps the brightest, most energetic supernova create a larger abundance of heavier elements than expected, and these play an important role even for elements heavier than zirconium. Or perhaps during the giant phase of an evolved star's life, a slow addition of neutrons allows elements to build their way up the periodic table, creating those observed heavy elements. However, each scenario, while compelling, has its flaws. There must be something else at play beyond what is known today. So the most responsible stance to take scientifically is to state that we don't know and must collect the critical data if we hope to find out. In a world-shattering revelation, astronomers announced last month that they may have detected a collision between a neutron star and a lightweight mystery object. An object larger than the largest known neutron star, but smaller than the smallest known black hole. The finding sheds light on objects that exist in this murky realm, which was long thought to be empty, but in recent times has revealed otherwise. More specifically, a signal detected in a pocket of the universe, roughly 650 million light-years from Earth, indicates a rare merger between a neutron star and what astronomers suspect is a surprisingly lightweight black hole. The pair would have danced around one another and merged about 650 million years ago, generating ripples in the fabric of space and time known as gravitational waves. These waves were sensed and flagged on May 29, 2023, by a network of antennas in Japan, Italy, and the US associated with the LIGO-Virgo-Cagra collaboration, or LVK for short. According to Evan Goetz, a LIGO researcher at the University of British Columbia in Canada, these are rare events. It's very exciting for the community to study as the first one of its type. The black hole candidate, which is about 25 to 45 times heavier than our Sun, is heavier than the established limit of 25 suns for a neutron star, but lighter than the lightest known black hole, which weighs about 5 solar masses. This places the newfound object within the mass gap, a mysterious region that separates the heaviest neutron stars from the lightest black holes. This discovery, as Michael Zevin, an astrophysicist at the Adler Planetarium, said, hints at this mass gap being less empty than astronomers previously thought. Black holes, small and big, are born from the violent deaths of immensely massive stars. A few models of how stars evolve, however, predict black holes with masses within the mass gap range cannot directly form from such stellar deaths. In Goetz's words, it does appear that it could be possible now with these observations. Perhaps astronomers need to tweak the models, or maybe we really do have a more complicated evolution of a heavy neutron star that evolved into a black hole. It's hard to know just from this one example. In early 2020, astronomers announced the first conclusive detection of gravitational waves created by a collision which involved a stellar remnant right in the mass gap range. However, the discovery team couldn't classify the object with conviction at the time, concluding it could be either the biggest known neutron star or the smallest known black hole. As for the latest finding, astronomers say they cannot pinpoint just where in the sky the mammoth objects merged because only one LVK detector was recording data when the signal was detected. Nevertheless, the finding has raised hopes that there may be many more such mass gap objects out there waiting to be discovered. As Heather Fong, a LIGO researcher at the University of British Columbia, said, there is a lot more potentially we could find and a lot more to look forward to. After a short maintenance break, LVK detectors resumed measuring ripples in spacetime on April 10th. The LIGO team anticipates observing over 200 gravitational wave signals by February 2025, including hints of a few objects within the elusive mass gap range. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.